Over the last few lectures, we had been primarily talking about quantitative variables. What we will do in today's lecture would be to consider two qualitative variables or categorical variables. Now, when you have two categorical variables, say with M and Q classes respectively, then suppose we fix the first category of one class. Then the other categories of the second variable would be distributed along this. So what is this distribution like? Is the distribution same for all the categories of the first class with respect to that of the second? This is the type of things that we'll be looking at when we do correspondence analysis. So correspondence analysis primarily looks at the association between two categorical variables, and we'll see how we can measure this sort of association or get plots which will tell us about the association between the variables of two categorical types. Correspondence analysis is a graphical procedure to represent association between two or several categorical variables. Of course, in this lecture, we will be primarily concerned with two categorical variables. The data usually is in the form of a contingency table which shows the joint frequencies or the counts of the two categorical variables. And the aim is to find indices that show the strength of the relationship between these two categorical variables. So it's primarily the association between the two categorical variables that we'll be looking at. Now suppose we call the two categorical variables x and y. And suppose x have m categories and y have q categories. So we have a m by q table of x values and y values. This is a contingency table represented by the m rows of x and the q columns of y. Now let xij be the frequency or count in the ij itself. That is, xij is the number of individuals with x category I and y category j. So for all these MQ cells, we will have this xij spread over the whole table. Let n equal to summation over I and summation over j xij. So n actually gives us the total frequency of all the individuals in the study. We define xij by n as bij, which is the proportion of frequencies in the ij itself. So Pij gives us the proportion in the ij itself for this whole table. Okay, so it's a proportion that is actually calculated over all n individuals. Typically, a table would look like this. This is an archaeological data obtained from Johnson and Wichern. On one side, we have the different types of potteries that we have found in the archaeological sites, and the other side we have A, B, C, D are the different sites. So there are 4 sites and 7 types of potteries that have been found in these 4 sites. And for example, let's look at the first cell. It has a number 30, which means that at site A, there has been 30 potteries of type 1. So if you look at the marginals here, the marginals in red, these are the totals over the rows and the columns. So let's look at the first row. The marginal total here is 89, which means that out of the total 781 potteries that have been found, 89 potteries were of type A. Now, this 89 potteries of type A have been found from the different sites, and these are distributed as 30 from site A, 10 from site B, 10 from site C, and 39 from site D. Similarly, if we look at the 6th row, it gives us the distribution of over the different sites of the type 6 pottery. So there are 120 such potteries found, and 45 of them came from A, 6 from B, 59 from C, and 10 from D. So these are referred to as the row profiles, and we'll look at them in details. Similarly, if you look at the columns, let's look at the second column here. Here we look at the site B, and what we look at is the type of pottery that we find in B. There are 10 of the type 1, 4 of the type 2, 1 of the type 3, 4 of the type 6 of the type 4, 36 of type 5, etc. And there has been, out of the 781, 91 potteries that have been found at site B. So this gives us the distribution of the types of potteries that have been found in site B. Similarly for the other columns. What about the marginals? Look at the column, last column, which gives us the marginals of the rows. So in this case, we have 781 total potteries found, of which 89 is of the first type, 75 of the second type, etc. Similarly, if we look at the last row, again there have been 781 potteries found, and 283 are from site A, 91 from site B, 333 from site C, and 74 from site D. So this gives us the distribution of the potteries coming from the different sites. Now let's look at the proportions. How do you calculate these proportions? There are two ways that we can do it. First, we call this the row profiles. We look at the proportions where we divide by the total of the rows. So here each row element is divided by the marginal of that row, so that the total marginal comes out to be 1 for each row. For this we see that for pottery 1, 34% have been found in A, 11% have been found in B, 11% in C, and 44% in D. So this gives us a profile as to which site the first type of pottery comes mostly from. It's primarily from D and to a large extent also from A. Similarly, if we look at the last row, we see that of the type 7, only 7% comes from A, 13% from B, 78% from C, and 2% from D. And we can readily say from this that C and 7 are closely related. That is, the 7th type of pottery is primarily found in the site C. So this row profiles actually helps us to find in which site we would be finding the particular type of pottery. And then finally what you have is the last column, where you have the distribution of the masses. So if you look at the distribution of the masses, you'll see that the first pottery type is 11%, the second 10%, and similarly the 7th is 28%. So you can see that the 7th is the most abundant of the pottery types that we can find over the different sites. And then also we see that how they are distributed over the sites. These are referred to as the row profiles. Similarly, we can have what are referred to as column profiles. In this case, of course, we'll be doing the column sums and dividing by the column marginals. So you can see that the column marginals now are 1. And what we look at a particular column. Say for example, the last column D. It says that 53% of the potteries found in D are of type P1. Only 3% are of type P2, 1% of type P3, 5% of type P4, 18% of type P5, 14% of type 6, and only 7% of type 7. So this is the type of potteries that we find in D. Similarly, we can look at these columns for A, B, and C, and this again tells us how the potteries are distributed over a given site. So which pottery is prevalent or more abundant in a particular site can be easily seen from here. Then again, if you look at the last row, it gives us the mass for each of this site variable. So we can say that 36% of the potteries found comes from site A, 12% from B, 42% from C, and 10% from D. So it gives us an idea as to how many potteries come from which site, etc. So as opposed to the previous row profile, this column profile provides us the distribution for each site over the different potteries. Row profiles, I repeat, where the distributions of the potteries, for each pottery we had the distribution over the different sites. For column profiles, for each site we have the distribution of the different types found in that site. Now what we typically would be trying to find out is to look at a plot like this, and this is a correspondence plot, and in this case what you see as the red marks are primarily the potteries and the blue marks which are primarily the sites, and the closeness of this tells us as to which site is associated with which pottery, as also it tells us whether the type of pottery is found is similar or their profiles are similar or not. We'll go into details of this later on. Before that, we need to find the mathematics behind this as to how we get this plot. Now, in matrix terms, let X be the matrix of frequencies. Remember, the frequency in the ij cell was given by Xij. So now we write this in a matrix form where we have M rows and Q columns. The rows, if we go back to the example, would be relating to the potteries, and the columns would be relating to the sites. So in this case, if you go back again to the example, M would be equal to 7 and Q would be equal to 4. And we get the proportion. So remember, here we are dividing the elements by n. So the matrix P that we get is X by n. This is the matrix of frequency proportions. Now define as a vector R, where the elements are R1, R2, Rm. So it's an m-dimensional vector. These are the marginals for the rows. Okay, so marginal based on the proportional frequency. So Ri is basically sum over j, Pij. So it's the ith row total of P. Similarly, the column totals are given by C1, C2, Cq, and these are written as a vector C of dimension Q, where again Cj is the sum over I, Pij. These are the column totals of the frequency proportions. Now without loss of generality, we'll be assuming that M is greater than Q. Why we say without loss of generality? Because it doesn't matter which you call as your first variable and which you call as your second variable. So we can always call x as y and y as x. So we can interchange this, and we'll assume that the number of rows is greater than the number of columns. Of course, you can always interchange this. Now we'll define Dm as a matrix, a diagonal matrix consisting of the row totals. So Dm has off diagonal element 0, and on the diagonal you have R1, R2, Rm. So it's a m by m diagonal matrix. Similarly, we define a diagonal matrix Dq consisting of the column totals C1, C2, Cq. So again, this is a q by q matrix. Now correspondence analysis relates to the problem of finding a specified reduced rank matrix P star, or the elements of which are small pij star, which minimizes the sum over both I and j, Pij minus Pij star square by the marginals Ri into Cj. So what does this give us? This gives us that we are making an approximation to this. Okay, so instead of the full rank, we are looking at a reduced rank matrix P star, such that the difference in the elements between the original matrix P and the matrix P star, the elements of this, we look at the squared distance of this, normed by the row total and the column total. We would like to minimize this summed over all the variables. Okay? So this actually would give us an approximation of P by P star. Now if this value is small, then the approximation is good. And if we can get a good approximation, remember P star is a reduced rank matrix. So we can approximate the full rank matrix by a reduced rank, and hence we can reduce the dimension of the study by looking at just the independent columns or rows of this new matrix. Now this value actually can be written as the trace of dm to the power minus half p minus p star dq to the power minus half into the same thing transposed. Mind you, it's a square, so we take this, its transpose, and then take the product of these two matrices. We then take the trace of this. Now, using what is referred to as the singular value decomposition, remember this is not a square matrix. So, using a singular value decomposition, we can write P as summation j equal to 0 to q minus 1 lambda j dm to the power half uj into dq to the power half bj prime, where the lambda j's are the singular values of dm to the power minus half p dq to the power minus half, and ui and bj are the corresponding singular vectors. Remember that we have assumed that q is less than m. So when you do the singular value decomposition, the number of terms should be q. And we are assuming that j runs from 0 to q minus 1, which really means there are q terms in this. One reason why we take j equal to 0 to q minus 1, we'll explain later on, because it's easy to understand that way. So there would be q terms in p in the singular value decomposition. What we then do is, we look at the reduced rank approximation to P, and this is given by just the first k terms of the values of the expansion that we had on the right hand side, provided of course the lambdas are ordered. So remember, we have ordered the lambdas, so lambda 1 is greater than lambda 2 is greater than lambda 3, etc. So once the lambdas are ordered, so we'll be looking at this ordered values, and we'll take the first k terms, and that would give us a very close approximation to P. Now, it can be mathematically shown, and I'm not going to prove it here, that R into C prime, remember R is of dimension m and C is of dimension q, so RC prime is a m by q matrix. We can show that this is the best rank 1 approximation to P, and hence we take this as the first term on the right hand side. So we bring RC prime out as the first term on the right hand side, and so now instead of summing from j equal to 0 to k minus 1, we sum from j equal to 1 to k minus 1. And the problem now becomes finding the singular value decomposition of P minus RC prime. We take the RC prime term to the left hand side, and instead of looking at P, we are now concerned with looking at P minus RC prime. Remember, like P, RC prime is very readily obtained from the marginals of the rows and the columns. So we take that out and try and approximate the remaining terms. That is what we'll be trying to do. Now, owing to the orthogonality of singular vectors, remember, corresponding to the singular values, we have the singular vectors, and the singular vectors are orthogonal among themselves. So if you look at P minus RC prime, it will lead to the same sort of expansion with the remaining lambda j's. What we do is, we discard the last s minus or q minus k lambda j's, what we do is we take p minus r c prime, and this is approximated by the first k minus 1 terms of the q minus 1 terms remaining. So we discard the last q minus k terms and just retain the k minus 1 terms. So the best approximation of order k or rank k to dm to the power minus half p minus r c prime dq to the power minus half is given by summation j equal to 1 to k minus 1 lambda j uj vj prime. So this gives us the best approximation. And what is the error remaining? The error remaining is the terms that we have omitted, and that would be the same sum j now from j equal to k to q minus 1 lambda j uj vj prime. That's what we have left out, and that would be the difference between p and p star. That would be the error committed. That's where the approximation is. And if that is small, then p star is a good representation of p. Note that dm to the power half uj, dm to the power minus 1, dm to the power minus half uj, you can simplify this. It becomes uj prime uj, and that is equal to 1 because these are normed vectors. And similarly for vj prime vj equal to 1. So these are of unit length. Now, how do you actually find the axis? So let capital lambda be equal to diagonal lambda j. So capital lambda basically is a matrix formed by the singular values. And let capital U be U1, U2, Em. So it consists of the M vectors U, J's, and this is a matrix that we have. Similarly for V, we have a matrix V, which is V1, V2, Vq. So these are the matrices of singular values and vectors. We then define f equal to dm to the power minus half, dm to the power half uj into capital lambda, and similarly we define g. Now what f and g contain respectively are the k minus 1 dimensional coordinates corresponding to the m categories of x and q categories of y. Now usually the plot is based on 2 or 3 dimensions. The 2-dimensional coordinates of m would then be given by the categories in x by the rows of lambda 1 dm to the power minus half u1 and lambda 2 dm to the power minus half u2. So if you look at this carefully, you see that dm is of dimension m, and you multiply this by u1, you get a vector of dimension m. So the first one is a vector of dimension m multiplied by lambda 1. The second term lambda 2 into again a vector of dimension m. So we have pairs. We have two sort of, the first element of the first vector and the first element of the second vector gives us the coordinates of the first category of x. The second element of the first vector and the second element of the second vector gives us the coordinate of the second category of x. And similarly, we get the coordinates of each of the categories. If we wanted to do a 3-dimensional plot, we would have taken a third term that would have been lambda 3 dm to the power minus half u3. So that would have given us a 3-dimensional plot. But generally 3-dimensional plots are difficult to look at, so we have restricted ourselves to a 2-dimensional plot. Similarly, when we look at y, we look at the rows of lambda 1 dq to the power minus half v1 and lambda 2 dq to the power minus half v2. Again, dq is of dimension q. So if you look at this, this becomes a matrix of dimension q by 2. And the first row, the 2 elements in the first row would give us the coordinates of the first category of y. Similarly, the second row would give us the coordinates of the second category, and similarly the qth elements would give us the coordinates of the qth category. So this is what we actually plot in a correspondence analysis plot. And this is how the plot is done. So if you look at the previous slide, the first lambda 1 components actually come into the rows here, and the second component comes into the columns here. So one is the x-axis, the other is the y-axis, and we have a symmetric plot here. And you can see several things from here. Firstly, if you just ignore the blue dots here. So remember, the red dots are the potteries. You can see that P2 and P3 are close together. So we can say that the profiles of the potteries P2 and P3 are similar, whereas the profiles for potteries 1 and 7 are vastly different. They lie very far away from each other. So this is one thing we can say. If you look at the blue dots now, we can see that B and C are relatively close, whereas D and C or D and A are very far away. In fact, D is very dissimilar to both A, B and C. So it's somewhat different in the nature of the site D. Next, again, what we can look at is how the red and the blue dots lie. We see that P1 and D lie very close together, which means that pottery 1 probably is abundant in D, whereas pottery 7 lies very far from D. So if you look at the relative frequencies, the 7 type of pottery is very seldom found in D. So again, the association between the two variables can be given by this layout. This is what the actual analysis goes into. Associated with this, we look at the total inertia. Now, what is the inertia? Now, we are looking at a number of variables which we are concising into 2 or 3 dimensions. So, how does the variability match here? How much of the variability do we capture really in this smaller number of dimensions? The total inertia or the variability in this data is given by the observed minus the expected frequencies, which is Pij minus Ricj square by Ri into Cj summed over both I and j. And this, as you know, is basically the chi-square statistic, chi-square, and in this case, of course, you have a divisor n. But you can also show that it is sum of the singular values squared. So it's lambda j squared summed over I equal to 1 to q. Now, the inertia for the jth dimension is given by lambda j square. That's the corresponding singular value for the jth component, and we square this. Thus, for each of these dimensions, the inertia is, for the first dimension, it will be lambda 1 square by the total sum of the inertias, that is Te. For the second dimension, it would be lambda 2 square by the total inertia. So for a two-dimensional plot, the total inertia that is actually accounted for is lambda 1 square plus lambda 2 square divided by the sum of lambda j square over j equal to 1 to s. And this is large. Then the two-dimension actually captures most of the variability in this data and is thus a good representation. So if we do a two-dimensional plot and if we get the inertia as a large quantity, as a large percentage, it really means that we have been able to capture most of the variability in the data and a plot is a good one. If this is small, then the representation is not good enough. So for the data that we had looked at, the inertia for the first component was 0.2836. For the second was 0.1701. We didn't calculate the third, but it was 0.0588. And if you look at the histogram, you can see that on the right hand side, the number of stars are large. That tells you that most of the inertia was captured by the first one. And you see that it's 55%. The second one captures about 33% and the third one 11%. So the first two together captures 88% of the total inertia of 0.5125. And therefore, we can say that for this, a two-dimensional plot would give us a very good idea. So this is what we would be looking at. Primarily, the final plot in correspondence analysis, which shows us how the two sets of variables with different categories are associated among themselves. In today's lecture, we considered correspondence analysis. In this, we saw how we can find association between two categorical variables. It gives us an idea as to what the profiles are like for each of these categorical variables as well as how they are associated. We also found how we can actually do a plot of this and what the amount of variability that is explained by this two-dimensional or three-dimensional plots that we have. So correspondence analysis primarily helps us to find the association between two categorical variables.